so, um, so let's see. So as I'm doing this, so let's look at the schedule. So so we have two or three more lectures on like dimensional reduction, and then we'll talk about some noise and some privacy issues, and then we'll finish up with stuff on graphs. So the lecture on Monday, which is the next lecture, I won't be able to be here live actually. So I'm supposed to be traveling the first part of next week. I've been told I'm still traveling virtually. It looks like my meeting is East Coast and will be done in time for me to give the lecture on Wednesday. But so Monday I won't be able to. I'll be done around 3:45 that day. So my plan is to try and come on Thursday and so okay, so is to try and come on around 4 o'clock or so, and so answer some questions. Oh, okay, great. So there's a question: can we go over the differences on question 1C and 1D for the homework? Yeah. So a number of people have been having questions about homework 6. Okay, so Benwei says he's recording locally. So if we aren't able to get this live on YouTube, then we'll use Benwei's recording, and we'll have we'll have to upload it later. So Benwei, if you can also post on Canvas, just to say that the live stream on YouTube is not working. So okay, so homework 6. So question. So you're given this problem in regression, and you're asked to look at this data set. And in question B, I ask you to split it up into 3 test and training sets. And then to use cross-validation, basically by you should basically looking at the average prediction across all of the test sets which you filled out, to try and select the best value for S, where if using ridge regression, you have this extra you have this extra parameter you have to choose with cross-validation, right? And so then C is asking you to choose which value of S is the best. So in doing this, right? And then question D is then asking, well, I want you instead to do something else with cross-validation, which is to look at the average error and predict the error you'd get on one new data point from the same distribution, right? So if you were to get a new data point from the same distribution, kind of predict how much squared error you would expect to do in that. And that's pretty much the same procedure as before, but for a fixed value of S. And so as I mentioned in class, there are 2 uses of cross-validation. One is to choose parameters. One is to predict generalization. And so I'm asking you to do I'm asking you to use the results from B to do both of those, right? To choose the parameter in C and to predict the generalization error in D. Then D, but the issue is, okay, then D has a second part, which is what is problematic about the above estimate, especially for the best performing parameter value of S. Okay, so I'm not going to totally give you this answer, but this is something we talked about in the lecture on cross-validation. If you're doing if you do any one of these things, it's fine. But if you read this carefully, there's an issue, and then there's also some assumption you need to make in E, right? So I'm hoping the answer, ultimately the answer is very simple. I'm hoping this this clarifies what's going on. Okay, could you please minimize the recording panel? It's covering. Oh, yeah. I'm not. If I don't touch anything, it should. Oh, okay. If I move my mouse off there, it does that. Great. Thanks. Right. So okay. So the answer isn't very complicated, but I want you to kind of, this point I'm asking, I think, is important, and that's what these questions D and E are supposed to be covering. So great. And then I'll also mention, if you look at the schedule, I posted the homework for dimensionality reduction, which is here. This is due on April 8th, which is in 2 weeks. I've kind of trimmed the homework down from what it typically is by a small amount. I'm hoping it's pretty simple. The first one asks you just to compute the SVD and analyze things about the norm of the matrix, right? There's some, I suggest you do this in Python, although you could do it in MATLAB or R. It's probably a little bit simpler, but just to keep coherent, I've kept everything in Python, and I've given you pieces of code, so it should be really straightforward. The second part, I'm asking you to implement the frequent directions algorithm for large-scale matrix sketching, which we'll cover in the lecture today. And I've given you the stub of the code just to make it a little bit less intimidating in Python. You can do it in MATLAB or R or something else that may be a little bit more natural with matrices, but it shouldn't be too hard in Python. And then I moved other stuff into the bonus. All right, so hopefully this homework isn't too challenging. You should be able to start it kind of with what you have already. So with some issues, oh, YouTube just sent me an email. They have issues with, oh, that's from Benwei. Okay, so let me try going live one more time, and then we'll start the lecture. Oh, okay, and then, yeah, I still haven't totally decided what to do with the interim test. I'm probably planning to, there are two options. One, we can do this ProctorU thing where it would be just like the regular test, but you have to have a secure internet connection to have your video turned on the whole time. Or I can just make it take home a longer period. Probably a little bit harder if I did that. So if you have strong opinions, you can, please let me know either way. For instance, if it's hard to get a secure internet connection with video the whole time, then and if that's more than a couple people, then we should probably do the take-home test. And then we'll figure out what to do for the poster stuff as well. And if you missed it, Monday's lecture will also not be live, unfortunately, because of some scheduling stuff scheduling issues I have. Okay, so let's get into the lecture today. And we're going to be talking mostly about these matrix sketching ideas, which is about mostly about how to do stuff like the SVD approximately, but at very large scales, and what are the trade-offs you get there. And you're not going to get it exactly, you're going to get some approximation there, and we'll look at what those approximations are. There are algorithms like the other streaming, these will be a streaming algorithm like the other streaming algorithms like niche-agrees and count sketch, count min sketch. These are going to be fairly simple algorithms kind of to port to a stream. But we'll just walk through them and understand a few of them and look at the trade-offs. All right, okay, but first, let me just review that a few things about where we started with before. We have an input as a matrix A, and this is an R n times D. So that means our matrix A, and will look like this. It's going to have these n rows, and it's going to have D of these columns. And usually in this class, we'll think about having more, the interesting case will be more rows than columns. You could think of this, the transpose, and a lot of the stuff holds where D is bigger than N, but we'll just kind of keep this more consistent. Typically, you have, think of each row as a data point, and each column is an attribute. Usually, to do good analysis, you usually want many more data points than you have attributes. Otherwise, you need to do something like lasso or something to help you try and sparsify it. All right, so but we're going to be talking today about the case where both n and d is big, and so some of this will apply in kind of in either case, but we'll think n is especially big and d is still larger than we'd want. Like n, we'll think of maybe n equals, say, something like it's like 10 million, could be much larger than this, and d is going to be something like so like 100,000, maybe it's 10,000, something like that. So n is still much bigger than d, but d is still going to be large. All right, and then to analyze this, we talked about this technique called the SVD, the singular value decomposition, and what this does is it breaks down the matrix into a product of 3 matrices. The first one, I drew this too big, these are supposed to be square, the same size. This is U. This one is S, and then you have another square one, which is V transpose. So the product of these 3 matrices, U, S, and V, I multiply them back together, I'm going to recover A exactly. That's what the decomposition means, but there's special structure in here. Particular, S only has kind of data on this diagonal. The rest is all, everything else here is zeros. And so that means that a big swath of U is kind of unimportant because it's multiplied by these zeros down here at the bottom, so that these aren't so important. But otherwise, the matrix U is going to be orthogonal, which means the columns are unit vectors, and they're kind of and they're each individually orthogonal with each other. And V is going to also be orthogonal. Now the rows are going to be the important thing, whereas in U the columns are, well, the rows of V transpose. And these are called the rows of V transpose are going to be the right singular vectors, and those are going to describe the best subspace of the d-dimensional space that we have, that we're analyzing, that captures the data, where the most variation of the data is. And then the kind of the singular values, these singular values in S are going to be decreasing value to tell you how important that subspace is. Right. Okay. And this gives us, by projecting onto the top right singular vectors in V, that's going to give us the best subspace approximation of the data in A. All right. Okay. There are a couple structural things I wanted to say before we kind of move on to the stuff on the matrix sketching. So the first thing is that we wanted to talk about the connection to eigenvalue decomposition. Okay, so the eigenvalue decomposition is more likely to have been taught in a linear algebra class than the SVD, but I view it as kind of a more restricted version of the singular value decomposition. But the relation between these is like actually very, very tight. Okay, and the way to think about this is there are two types of, so the okay, so what an eigenvalue is it the, okay, so the input to kind of this way of thinking is a square some matrix. We'll call this M, and for now we'll say this is in D by D, is a D by D square matrix. Okay, and then an eigenvalue and vector satisfies that. Okay, so this V, it satisfies this property that if I multiply this matrix M by this vector, so that this is a vector now in RD, because I have to be able to multiply it. If I multiply it, I get back a scaled version of this same vector. Okay, and for now we'll typically think of this vector as being a unit vector, and so then that gives you a value of, then this guy is going to be associated the associated eigenvalue. It tells you how much it scales it, right? If it scales it up more, so it's more important. If it scales it down, it's less important in some ways. And I guess those could be reversed depending on if M is like a Laplacian matrix, then this might be backwards. All right, and there's a similar decomposition property with eigenvalue decomposition, where you can write M as V L V, so V inverse, where V is an so where V is going to be orthogonal matrix. So now V inverse is actually going to be equal to V, and so or is it equal to V transpose? No, wait. Okay, so V inverse is going to be equal to V transpose, right? So we can write this as VL times V transpose, and V is going to be a D by D matrix, which is containing all of the eigenvectors. They're going to be exactly V, and they're all going to have to be associated with positive eigenvalues, where L is also going to have the structure, which is going to have lambda 1, lambda 2, up to lambda D, with zeros here. These are all going to be positive and real. These are all going to be kind of greater or equal than 0, and real if M is what's called positive semi-definite. And so this definition, kind of what this really means, is kind of complicated. One way of getting it is by saying, well, we're going to turn our matrix into this matrix M. Okay, so there are two ways of doing this. We can write MR for the right version of M is going to be equal to A transpose A, right? So now this is going to be a D by D matrix. Okay, or we can do ML A transpose, which is going to be N by N. Is V guaranteed to be fully orthogonal, or can we have its column vectors that aren't so unit length. Yeah, so it's the typical way you describe the the eigen decomposition and the way it's typically computed is that it has the columns of be completely orthogonal, the same way that we do this for V and U in like the singular value decomposition. This is for consistency, so otherwise you can scale V and also lambda and it's still an eigenvector. But for some simplicity, we'll just assume, and this is pretty typical that you assume that at least in these applications, that each of these is unit length. And that's useful when thinking about projections and all that other stuff. Otherwise, you have the scale baked into that as well. I'm going to put all the scale into L the same way I did with the singular value decomposition into S. Okay, so we're going to get these two matrices. Yeah, so we're going to get these two matrices, MR and ML, from A transpose A. And these are guaranteed to be, these are going to be positive semi-definite. Okay, so then we don't need to worry about these weird conditions with when the eigen values actually exist or not. Okay. Okay. So now, if I look at, let's start with MR, which is A transpose A, and I want to think about multiplying this by like an eigenvector. Let me make sure I'm doing this the right way. Yeah, so I want to think by multiplying this by an eigenvector, all right, and or let's say actually, let's do it by this entire matrix V, right? So what's going to happen here? I can think of expanding A by U S V transpose, which is the right singular vectors, which is the singular value decomposition of A. All right, and so what this will do is I'm going to get V S U transpose. I've done the transpose of A after I've done the decomposition. What that does is it switches the order of everything and it transposes all the matrices. S transpose is back to S again eventually, or essentially they're ignoring that it's N by D instead of D by N. And then this is U S V transpose, okay, times V. Okay, and what happens here? Well, U transpose U, these are orthogonal matrices, so these are going to cancel out. And I'm also going to V transpose V are also orthogonal matrices, so multiplying them, they're both full rank orthogonal matrices, so multiplying them together gives me the identity matrix. And this is the identity matrix. So what I'm going to get left is going to be V S squared. Okay, so what this is saying, that if I took this here and I multiplied it on the right of MR, which is my square matrix I want to do the eigen decomposition of, what I'm going to get back is V again times the singular value squared. Remember, this is going to be S is still going to be essentially a diagonal matrix, but now all the entries, when I square that matrix, what I'm doing is I'm squaring all of the entries. So S squared is going to be equal to sigma 1 squared, sigma 2 squared, up to sigma D squared here. Okay, and so what this means is that the right singular vectors Vj of A are the eigenvectors MR and the singular values squared, sigma I squared, is going to be equal to the eigenvalues. Of MR. Okay, so the right singular vectors and the eigenvalues are basically the same thing. So I'm just doing this when I don't need to have a squared matrix as my input. I get the singular value decomposition, and I get something different on the right or the left. And if I do the same thing with ML, right? If I look at the matrix ML here, I have at the bottom. I'm going to map these to U, but also S squared, right? So I'm still going to get the same singular values here. A bunch of them are probably going to be 0 because it's not full rank. But the singular values are the same for MR and ML associated with them. So the eigenvalues are going to be the same for MR and ML. And U is now the left singular vectors are going to be the eigenvectors of ML when I do this n by n matrix. Okay, and that's why the ones after the first D don't matter so much again, because they're going to be associated with 0 eigenvalues. But they just fill out the matrix to make it square if n is bigger than D, right? So if you see the eigenvectors and values before, hopefully this helps give some insight into what this singular value decomposition is if you haven't seen this connection. Right. So then Max, I'm giving you a lecture here. You have to leave. Okay. Then you say bye, okay? Okay. Thanks. So then the other thing we say, the other thing we talked about is to find the subspace B, say k-dimensional, which and I represented this as V1 up to Vk to minimize the sum of squared errors from A to B, which is equal to sum of I equals 1 to n of AI minus the projection onto B of each AI squared. Oh, where'd that go? Okay, right. So so this was the other thing we wanted to do, and so now if we say B contains the origin, then the SVD is the optimal thing to do, right? So we have all these vectors V1 through Vk, but they're implicitly a vector from the origin, so it defines a subspace that is containing the origin, right? So we have these vectors V1 and V2, but remember they were starting from this point on the origin, and so this is fine if your data is kind of centrally located around the origin, but if your data points lie kind of like this, right? So they're not going through the origin. I'd rather find a single subspace that passes through here, right? So all the data points are close to this one-dimensional subspace here. But these points are not through the origin. And this happens in a lot of applications. For instance, you're generating high-dimensional vectors, and all the values have to be positive, right? If you're doing kind of one of like these like bag of words representations, where I'm doing counts of all these vectors, all those counts have to be positive, right? So they're not going to go through the origin, they're going to be in the positive orthant, and I want a subspace that's not restricted to go through the origin. Especially if I'm going down to like from 100,000 down to like 300 dimensions, it doesn't matter so much. And with one extra dimension, I can throw the origin in there without too much. If I'm going down to 2 dimensions, this makes a big difference. And this is important when you want to kind of draw a picture and visualize what things look okay? So I want to somehow find this blue subspace here that does not go through the origin, and this is the problem which is solved by principal components analysis. Okay, and so the solution is simple. The solution is first we just need to center the data. Okay, so what this is basically doing is that here, let's take this picture. Okay, I'm gonna copy it, paste it. Okay, now I'm gonna take this guy here, and I'm gonna okay, that's not working quite as I wanted, but I'm gonna do this, and I'm gonna shift it so that it goes through the origin. Okay, that was a fun little experiment there. But I'm moving it, so I want to move all the point sets so that it contains the origin, and then I can run the SVD again. Okay, so in order to run in order to center it, it's pretty simple to do. I need to for each dimension j, remember these are in 1 up to d, I want to find some average value. Let's call this a bar j, which is going to be 1 over n. So I'm adding over n data points here. Sum I equals 1 to n, aij. So I'm taking this average of all the things in this column of A, right? So remember, I've got this matrix A here. And so what I'm doing is I'm taking the average over this one column, we'll call this aj, and the average with a 1 over n transform kind of over the sum is going to give me aj bar. Okay, and I'm going to do this for all of these things, and this will give me a single vector a bar, right? So a bar is going to be a1 bar, a2 bar, up to a d bar, which is just the average of everything in the column. And this is going to actually give me this point, which is right here. That's in the overall average of this data. This is going to be a bar, right? This overall average of the data. And then I just want to subtract this from all the data points. So then I'll say a tilde is going to be for ij, is going to be aij minus aj bar. Okay, right, so I'm going to take the original value aij. So for everything in this blue column, I'm then going to subtract the average. And what this does is it's this transformation that moves the data points, shifts them, right? So they've gone from, say, up here, and it shifts all of them. So this average point moves down to the origin. If I think of this is a vector going up to a bar, then I'm subtracting it, that's shifting all the points down onto the origin, or shifts them towards the origin, whichever way that is, right? So this is all I'm doing. So here, this is called this is called centering the data. And I'll just mention I can also do this through a trick which is called the centering matrix. Here, let's just write this on the next slide. Okay.
Sorry, Jeff.
Yep.
in the previous slide, the summation index should be I, not J.
Yeah. Great. Thank you. Right. This should be over I. Thanks. Great. Okay. So I can also do this through a centering matrix. I can define Cn is going to be the In. This is the identity minus 1 over n times 1. If I can write these a bit better. 1 transpose, where this 1 matrix is all ones. Okay, so this is this is called the centering matrix, and to do centering, one way of doing it is I can write A tilde equals Cn times A. Okay, so this just, it's a linear operation, so I can do A times the identity, so if I expand this out, this is A minus 1 over n times these all ones matrices times A, and this is basically computing the average and subtracting it. But linear algebraically sometimes is useful to write this when we do NDS on next week, then it'll be more convenient just use this. We'll talk about double centering, which is applying this twice. Okay. So once I do this, then I just do the SVD of A. This gives me U S V transpose. Maybe put these with the tildes, and then V T tilde. These are going to be the principal components, and these are going to be the principal values. And the way to interpret them is basically the same as with SVD. The V times the principal components give me the best subspace, which is defining the data. Principal values tell me how important these are, and they're in decreasing order of importance. And if I take the top two and project onto these, then this gives me the best two-dimensional embedding that does not necessarily need to go through the origin. Okay, one thing to keep in mind is you also, if you want to reconstruct this, I need to also kind of store this A bar vector, which is also in RD. So I'm not really saving any space, but if I just use the top principal components, that gives me a better two-dimensional or three-dimensional embedding, if that's what I'm after. All right, so that's the difference between this is, this here is called principal component analysis instead of SVD. Sometimes the literature will confuse these two things, but this difference can be important, especially in projecting very low dimensions. All right.
Sorry, Jeff.
Yep.
You are missing tilde on the top of A in SVD.
This is, yeah, here, great. So thank you, great. SVD and A tilde, great. Okay, so this was the remainder of the last lecture I didn't quite cover. So hopefully this is a good kind of a reminder of the core of like dimensional reduction. We'll see one other technique by doing these random projections, which will give us different guarantees, and we'll see that the second lecture next week is the starting point before we talk about noise. All right. Okay, so the next one. Yeah. So if you want to ask a question, go ahead.
Yeah. So I'm just having a hard time seeing the difference.
So the difference between what? Hey, how about you go ask Mama, okay? Can I give you here? You can sit here while I explain this, okay? Yeah, be quiet though. All right, can you ask that again, Richard?
Yeah, the difference between PCA and SVD, is it just that you apply the center on the matrix before you run it through SVD?
Yeah. So that's it.
Okay.
Right. So that's the only difference. SVD is kind of a linear algebraic operation. PCA is the best way to get this k-dimensional subspace that represents the data. And the difference is in the picture here, when the data points aren't near the origin, then you really want to use the PCA instead of just doing the SVD.
Right.
If the data happens to be centered, like in the example I did on Monday, then it's not going to matter too much. Yeah, or if you're getting down to like 300 dimensions, it's not going to matter too much. But for very low dimensions, it's important. Yeah. So okay, good. So so the next thing we want to talk about is very large scale. Okay, so typically to compute the SVD, so the SVD takes O of n d squared time if n is larger than d. Otherwise, you can do it in n squared times d time as well. So this is kind of the main, and so if we go back to when n is like 10 million and d is 10,000 or 100,000, this can be, it takes a long time just to read the data. And if d is 10,000, you're spending an extra factor of d, extra factor 10,000 to do this operation. Not only that, but these typically require kind of the data, the typical implementations require the data to be inside of memory. And so if your data is so big that it only fits on disk, you can make a pass and read it, but you can't fit it onto memory to actually, in order to actually do this. So there are ways to do this kind of in a distributed way. And so if we do the MapReduce lecture, we'll touch on a few of these ideas. What's been more recent, what people have done is a more machine learning approach to say, look, I don't care about the exact thing. I can drop the smaller singular vectors and values. And I'm willing to do a little bit of approximation because of all the modeling that has gone on. So anyways, so can I do this faster? Right, so and what they've done is they've looked at these streaming algorithms, and so when we do this with a matrix, we have a matrix A. Remember, n is big and d is not quite as big. Then the stream typically. Hey Max, can you go with Mama now? Feel better? Okay. So then. Then the stream is basically looking at one AI at a time. And so how you store the matrix in memory could differ, but a common way would be to either store it one row at a time or one column at a time. We'll be talking about the case where you're storing one row at a time. There are lots of different models of how you might store it. But this one is kind of the most natural generalization. And so we'll be talking about this. So I want to maintain, now think of, as I'm doing this stream, I'm reading one at a time, and I have some small space here, and I want to only use a small space to actually compute something like the SVD. And maybe I don't care about the whole SVD, maybe I just care about the output here is only going to be approximately some hatch version of S and V transpose. The U matrix is going to be n by n. I can't possibly store that. So I'm only going to worry about the singular values and the right singular vectors. Okay? And so I want to do this in small space. And so before we get into approximation, if D is reasonable size, where if D squared fits in, in the memory, then there's a simple way I can do this. And hopefully this also kind of gives some insight into how these computations work. What I can do is I can have a for loop, I equals 1 up to n, and I'm going to just store some matrix B. So I'm going to start with, let's start with B here, and this is going to be start with an all zeros matrix, which is D by D, and then each step through this for loop, I'm going to say B is going to plus equal AI transpose AI. Okay, maybe I want to do this, put the transpose on the other side. But the point is, this is going to be is an outer product of AI. It creates. I'm doing AI, which is a D by 1 vector, and I'm doing an outer product to create a D by D matrix, and I just add all these up. Okay, if I do the in the end, right? So if I return B, well, this is equal to exactly MR, and then the eigen decomposition of MR will give me the right singular vectors and the squared singular values. I can take their square root, so they're all going to be positive if I did them this way, right? So if D fits in memory, I can D squared fits in memory. I can just do this and then effectively do the eigen decomposition at the end of the stream, and I can get everything I want out of this. Okay, so if D squared is not too big to fit in memory, then this is the right solution. There's no approximation, and this will actually scale pretty well because it's well, it's a factor D times the so times the cost of reading all the data. Okay. All right. Okay, so I can do this exactly this way, but if D squared again is too big, let's say it's 100,000, 100,000 squared is bigger than I want to fit in memory. I don't want to pay 100,000 factor. Okay, so now if let's say if D squared is too big, but let's say D times K is kind of okay to fit in memory. Okay, and in fact, so I'm going to use slightly more than DK space. This is the size of the output anyways, so this seems very reasonable. I'm going to need a little bit of slack in order to compute this. So if DK maybe times 10 times DK is going to be okay. And I'm going to pay an extra factor, roughly 10 times K in the cost instead of a factor D times the cost of reading over the data. And so this is going to be called the frequent directions algorithm. Okay, and so what this is going to be doing is scanning over the data and now maintaining a sketch. And this is basically going to be the Misha-Gries sketch, but for a matrix. Okay, so I'm going to be maintaining something like a set of counters, but they're not counters; they're going to be vectors instead. And then if things get full, I'm going to have to shrink them a little bit so I have space again. Right? This was the idea of Misha-Gries with counters, but we have to be more careful. In this setting, we'll have to maintain some orthogonality of the counters, right? Or the vectors that we're actually maintaining, and we'll do this through the SVD again. Okay, so let me write down this algorithm, and then we can discuss it. Okay, so I'm going to set so step 0. I'm going to set some sketch B is going to be zeros. And now it's going to be a 2L times D matrix. Okay, think of L as, actually, let me just do it with L here. We'll put a 2 in front. I'll explain that later. L is going to be equal to K over some epsilon. Epsilon, think maybe if I have 10% error, then epsilon is going to be 10, right? So that's where this vector 10 is coming from. So this is going to be my sketch. And then I'm going to have a for loop for all a, I, and a. I'm going to do something. Okay, and so now I'm going to insert AI into an all 0 row of B. Okay, so I'm going to maintain that through the sketch, right? I'm going to have kind of A here. This is really, really tall and skinny. And I'm going to be maintaining some kind of up through some point here. I'm going to be maintaining a sketch B, which is going to have the same dimensions, probably even shorter, right? It's a sketch B here. It's going to still D dimensions up here. This is still going to be N, but this is going to be L. Okay, and I'm going to maintain that it's got some rows in here. Some of the rows, particular at the bottom, are going to be all zeros. Okay, and if I have, I'm going to always have at least one of those rows in there. Okay, and if I'm going to insert AI into one of these rows. Okay, so this will be this is inside this for loop here. Okay, now I'm going to say if there are no more 0 rows, okay, and I know that each time I'm going to use up one of them, so I can just keep a counter to see if I've used up all my 0 rows. Then I need to fix it so I get those 0 rows back, and this will be like the shrinking step inside Misha Greaves. Okay, so step 4, which is now going to be inside this if statement, is I'm going to compute the SVD of B, but this is okay. B is a much smaller matrix than A, so this I can do more efficiently. It still costs DL squared time, but it's not going to be too bad. Okay, I'm going to set this value delta I equals sigma L squared. So I'm going to look at the smallest singular value, okay, square it, okay. I'm going to set S prime. I'm going to update my singular values now as going to be, it's going to be it's going to be a diagonal matrix. And so the first one is going to be S1 squared minus delta I. The second one is sigma 2 squared minus delta I square root up to, and then the last one is going to be 0 because it's going to be sigma D squared, sigma L squared. They're only going to be L of these values. Sigma L squared minus delta I, which is equal to sigma L. Okay, so the last one is, is going to be 0. Okay, now I'm going to set B is going to be equal to S V transpose. Okay, which is, I'm going to ignore U. I don't care about the U part. I just care about the S and V transpose. Okay, and so this is going to be my updated sketch, and this is going to guarantee that the last row of V is going to be all zeros. Okay, because I'm multiplying by S prime, and I've shrunk this, and I've shrunk all of them, but in particular, I've shrunk the last one down to 0. So when I multiply it through by the orthogonal directions, which captures everything, then the last one will be multiplied by 0, and that'll guarantee that that this here guarantees that this last row here is going to be zeros again. So I'll guarantee if when I get the next row, I can fill it in. Okay, and then out of these for loops, and then I can return. I can return B. Okay, so this is the algorithm. It turns out this algorithm, as I've written it, is going to be n times d times L squared time. The runtime is going to be O of n times d, which is the time to read the matrix, times L squared, because every step through it, I have to run this step, which is going to take, this step here is going to take d L squared time. So every time I read a row, I'm allowed to spend d time, but I spend an extra L squared factor. I can fix this by putting a 2 here, so I double the space. But now I'm going to have the last L plus 1 rows are all going to be set to 0 by doing this. This one is still L. The still L singular value is set to 0, and the L plus 1 last ones are all set to 0. So if I amortize this step over every L steps, then I only take the SVD over L steps, and this goes down to O of n d L time. Right. So now the time is only about, you know, an extra factor k over epsilon, which is what this L term is. Okay, and I'm going to get an approximation similar to the Michel-Gries approximation of the matrix, but and it's going to have guarantees the same way Michel-Gries has guarantees that, and for the guarantees it gets, you can't use asymptotically less space. There are kind of proofs about this for the streaming algorithm. In fact, it was in a paper I had a few years ago. All right, so this is kind of if we're in a certain sense of approximation.
There's a question.
Yeah, go ahead.
Yeah, so I'm just wondering why you leave out U when you recalculate B in step 7.
Yeah, so all U is doing is it's rotating. It's telling you what the row space means. It's telling you what each row corresponds to, and that map requires that I effectively expand S with all zeros, and then I have an n by n rotation matrix rotating into that space. And what I'm doing here is I'm trying to come up with a low-dimensional representation of the aggregate of the data to represent this singular value decomposition. It's not, and so I don't need that information. I'm only trying to come up with what are the right projection directions and how much information do I have in those, and those are only in S and V, and so I don't need the U matrix in order to do this.
That makes sense.
If I want to actually compute this projection, I actually have to go back and do another pass, or there are, you know, some weaker guarantees you can do to try and do this on the fly, but that becomes a more difficult problem. But if I can make 2 passes over the data, then I can do a projection of all the data on the second pass. Yeah, it's kind of confusing that you don't need the U at all, but that's describing information that is not important for which directions are the most important here. Yeah. So let me quickly say what the bounds are here. Okay, so if I run frequent directions algorithm and I set L equals to 1 over epsilon here in this case. Well, let's say, well, so if with B equals, let's say 2L by D, then I'm going to guarantee that if I want to say for all unit vectors x in RD, then I can look at what this value is. I can multiply x by a and get some interpretation of how much variation there is in this direction x. Okay, and so I can show that I can approximate this by bx squared, and I want to know how big this difference is in between them. Okay, and I can say that this is always going to be ax squared is always going to be larger than bx squared, because I'm only shrinking the singular values of a as I'm computing this. But it's not going to be too much smaller. In fact, I can say that the error is bounded by a minus ak, the Frobenius norm of this, which is the squared Frobenius norm, which is summing up all the squared entries after I've done subtracting out the best rank K approximation, L minus K. Okay, so if I set L equals to, so if I set L equals to K plus 1 over epsilon, then this error is going to be epsilon times the, so the times effectively the tail, the part, the sum of the singular values after the K largest ones. So if the matrix is really close to being, most of its mass is, information is in the top K singular vectors, then I'm only going to get error relative to the part that isn't in the top K. This means that if the data is concentrated in a small dimensional subspace, I do an even better job of approximating it using this approach. So that's yeah, so that's great. Yeah, you can say some other error guarantees as well. I can also say a minus a times the projection onto the best rank K approximation of B. So I can take the best rank K approximation from B. Remember that L, which is slightly bigger than B, and I can project. And if I project A onto there, then I look at the error that's left. So this is my guess. Think of this as, right? So if I were to go back and project it onto the vectors I found and say this is approximately A sub K, right? So how does it respond? How is it similar to A minus A sub K? Then this is going to be L over L minus K. So now if I set L equals to K plus K over epsilon, then I'm again getting some sort of, then this is going to be less than epsilon times A minus K. So I'm again getting a good approximation of the subspace if I set L roughly 10 times K. So you can make these guarantees. You know, the specifics, I think you'll maybe play a little bit with these in the homework. The specifics aren't like too important, but this is one, at least for now, but this is one way of approximating, and it has these kind of strong guarantees. And like the Michigrees arm, you can't do it any better than this instrument. All right. Okay. Any questions on the actual algorithm? And then we're going to talk quickly about a couple of other sketching approaches that are more based on like the count sketch, which we talked about before, or just doing sampling and some other ideas. Right. So we scan over the rows one by one, and we maintain this matrix here B, and we maintain a bunch of 0 rows, which we know how many we have just based on using a counter. And if we just insert the rows into there, and if they fill up, then we have to do this step here inside the if statement that is doing the SVD and shrinking the squared singular values so that it is creating some space back in this matrix again. And by similar argument to Michigrees, a bit more complicated, you can show that the error, the error is bounded, and you can't kind of, because of drift in the data, you can't ever have these weird situations where the error accumulates. Yeah. Okay, great. So let me talk about a couple of other ways of doing this. Yeah. So right. So the another way of doing this is called is typically in this I'll call row sampling. Okay, and so in the literature, if you read papers about this, they usually call this column sampling instead, and this is where D is greater than N. They sample column stamp rows, but to keep this consistent, we'll call this row sampling. And what this is going to do is it's going to go again from our matrix A, and it's going to create a matrix B, right, which is going to be L by D here. Okay, and what the goal is to do is to select a set of rows here at random and put these into here. This blue one might go up here. This green one goes here, and this bright green one might go down here. So I'm going to fill up this matrix B now with these sampled rows from A. Okay, so it's a pretty simple idea. If I just sample the rows uniformly, I can't get very strong guarantees of how good of an approximation this is. Okay, instead, I want to sample the rows in one of two ways. I want to sample each AI proportional to its squared norm. Okay, so I want to basically give this a weight. Each row is given a weight, Wi, which is just the squared norm, and sample proportional to those. Okay, and I believe we talked about, so reservoir sampling, which is sampling in a stream. Okay, and this basically maintains a reservoir of things you've sampled as you're streaming through the data, and as every time you see something with probably the I thing 1 over I, you keep it and you throw something out of the reservoir and you replace it with this. This almost works just to maintain a reservoir size L, but this is actually trickier to do when you have weights. It turns out it's very easy to generalize reservoir sampling if the samples of size 1, okay, to having weights. You keep track of the total weight and you replace the one thing with the proportional to let Wi, this is uppercase, is going to be the sum equals, say, J1 up to I of all the lowercase weights. And I'm going to replace with probability lowercase I over uppercase I. So that's the probability I replace just a single thing, but I need to keep track of L of these, so I do this, do L times independently. Okay, so I do L of these weighted reservoir samplers independently. And so I could sample 2 rows twice. If I have a really big row, I might actually want to keep it twice because it's really important that all the norm that determines the singular value decomposition or the PCA result is going to be in one really big row. Think of it as one outlier data point. Maybe you don't want to keep your own outliers, but that's what you're optimizing for. But so this will give you the right answer if I do L of these independently. You can fix this. You can fix the duplicate problem with what's called with what's called priority sampling. And this is described in the book if you're interested. It's a pretty, not too hard technique. There's a couple of tricks you need to do because it turns out the really high weight things you want to keep with probability 1, and so you have to adjust some weights in a certain way. I'm not going to go through. So Paul, do you have a question?
Yeah. So it looks like to me that the main point of this is just to find the points with the greatest norm. Is that?
Yeah, if you just keep the points with the greatest norm, let's say I just kept, another way of thinking of doing this is I just kept a list of the points with the biggest norm, and I kept those all so completely deterministically, right? So there's no randomness involved. This does not work. I spent a summer internship once in grad school trying to figure this out, and it's still kind of not completely understood what can be said about this, but this doesn't work. You have to do sampling. The issue is otherwise you can have 2 rows which are basically identical and really big, and you'll keep both. But you might actually have a bunch of really small rows which are all pointing in the same direction. And so when you accumulate those all together, those are going to be more important. And so if you sampled, then you probably sample at least one of them. But if you just kept the biggest ones, you're not ever going to keep any of those small ones. So this is pretty similar to the k-means plus argument, that if you kept around, if you have a bunch of inlier points, then you want to sample those to be a center, but one outlier you might end up picking. And it's kind of the difference between those things, and so it's not quite the right thing to do. And there are cases where it's going to fail.
Oh, okay. That makes sense.
Yeah. And doing k-means plus or something like that in a streaming setting, that's kind of still an open question. There have been papers, but they're not quite satisfactory. Yeah, so these are very natural questions to ask. So, okay. All right, so this will give you a guarantee of something that looks like A minus the A times the projection onto B, and this is the full L-dimensional B, is going to be less than or equal to A minus AK. This does not need to be squared, plus epsilon times A. And this is if I set L equals to something like K over epsilon squared times log 1 over delta. There's some delta probability of failure in this. It's a randomized algorithm. Okay, so this term here is maybe not great. My error depends on the total norm, not just on the tail part, right? I'd rather have it depend on the tail, which have a much smaller Frobenius norm. There's a way to fix this, which what's called a leverage score, and I can change the weights I sample by this leverage score. Turns out this is tricky to compute, but there are ways to do it in a stream. If I just want, I might want to do this offline though, and then I can compute it. The advantage of this is B, the matrix B is maybe, it gives you a good low rank approximation of A, but it's maybe more interpretable. This is interpretable because now the rows are actual data points, where that's not true for doing PCA or SVD or frequent directions or the next thing we'll talk about for the next 5 minutes. So this is maybe a bit more interpretable as well. In practice, the space is not going to be as small as frequent directions for the amount of error you have, but you can do this faster. This will be a bit faster to implement. Okay, I want to talk about one more approach, which is going to be based on random projections, which we'll talk a bit more about next week, and based on the, there's a version of this based on the count sketch. So it's like the count min sketch, but you have this random sign and you take the median instead of the min, okay? So what I'm going to do here is I'm going to And I'll probably just tell you the algorithm because we're short on time, and we'll see it when we talk about random projections next week. We'll kind of understand a bit more why this is working. But I'm going to create a matrix. I'm going to think of creating a matrix S, which is going to be L times N. Okay, and each Sij is going to be drawn from a normal distribution. So a Gaussian random variable, which we talked about how to generate these for in locality sensitive hashing, scaled by N over L. I need to, this will give me the right scaling in my estimate. Okay, and so now my sketch matrix B is just going to be S times A, right? This is again going to be an L by D matrix once I multiply this together. Okay, so this is the idea of the sketch, and you can actually, because S is going to be, we're going to have this sketch matrix S. That's a horrible rectangle there. Let's draw this, and this is S, and it's going to be L by N. Basically, I can do this in a stream because as I'm streaming along in N, I just need to generate, to do this multiplication, I just need to generate this one kind of column of S at a time in order to do, in order to do this multiplication with what I've seen with A. So kind of the picture of what this looks like is I'm doing A, yes, and then I'm kind of multiplying it by this matrix S here, which goes off, and the result here is going to be is going to be B. And so I can kind of do this on the stream by taking the appropriate like the dot products of the rows of A as I see them. So we'll interpret this a bit more when we're talking about the random projection algorithm. I'll just quickly say a couple things and then we'll wrap up. So what I can do, so I'm going to say let A V K equals the best rank K approximation is basically the best. This is the best rank K approximation of V times K. So V is yeah. So and V is going to be the right singular vectors of B. This B which I'm getting out. Then I can say A minus A is the best rank K approximation times V transpose, right? So this will be, this is now my approximation of AK. This is, I can write a strong bound here at 1 plus epsilon A minus AK. If in order to do this, I need L approximately K over epsilon, right? So it's going to be some asymptotic bound again, and with some log minus log 1 for delta term. So I'm getting back close to what I got with frequent directions. Here, I can also give the stronger bound of 1. If I want to do this in regression, if I want to do this sketch and then do regression, I need a stronger bound, it turns out, because I need to approximate all directions. And for here, I'm going to get a relative error this kind of directional setting. This is for all x in RD. So the ratio between these is now 1 plus epsilon. Unfortunately, this needs this to be d over epsilon squared. So now the L is now larger than d. So I could have just done this times just done this this d by d approach. This is useful when I want to do this in distributed and these like MapReduce like settings we'll talk about later in class. There are some advantages in the stream, but we're not going to get into those. What this is basically doing is it's taking every row of A and it's kind of projecting it on a linear combination on parts of each of these rows. It's kind of this dot product, this kind of vector I'm getting here is telling me how much weight to put on each of these rows here, and it's distributing it. There's a different algorithm based on the count sketch where I take each row and I hash it into exactly one row, and I do a random sign. I either add or I subtract it. Okay, so this is based on the count sketch. And so this has various advantages, but for this, to get this guarantee, I'll need d squared over epsilon squared. These are useful, for instance, when A is very sparse, it's mostly zeros. And for very, very, very large matrix data, you're often going to have lots of zeros in A. And so then the matrix B will retain a lot of these zeros. And when I'm reading the matrix, I don't need to spend n times d time. I just need to read the non-zeros. Like in movie recommendations, most people don't recommend most of the movies. They haven't seen them. So you get these very, very sparse data sets. And this allows you to do this time proportional to the sparsity of the data. The sampling has that property, and there are versions of frequent directions, but they don't quite have this very strong guarantee needed to do sketching and then regression afterwards. Okay, great. So this is your kind of overview into matrix sketching, a pretty new area, probably only about 10 years old, but it's what people in large companies use for really, really large matrices to process them before they do some kind of try and interpret what's going on. So I can maybe take a couple questions, and then if you want to ask me more questions for like an office hour, probably around 5 o'clock, I'll be done with the last few feedback on the projects. I've got a couple more, so I'm gonna end this meeting in a couple minutes, and I'll switch over to the other channel. So great. So so that's it. I'll record the next lecture and I'll post it on YouTube probably Sunday night, and then I'll hopefully be around the 4:30 on Monday to answer any questions about it. All right, and then we'll go back to Zoom lectures after that. Is the plan. All right, great. Bye.
Thank you.